First and foremost, we have the gate that is this terminal over here in this device. And these other two terminals are what we call symmetrical because they are interchangeable. These terminals are called the drain and the source, and we differentiate between them for the nMOS device. When the drain is higher than the source, this is going to translate to this. And for the source, we are going to draw an arrow here. You're not going to see GDS drawn on a device, only an arrow that shows to us which is the source of the device. This is not standard because if we see a circuit drawn like this, we might rush to conclusions and say, okay, this is the source. But in reality, there could be situations where the voltage here is higher than this voltage and the arrow would mean jack shit. This arrow tells me that the current flows from the drain to the source and flows from here to here. And there is actually a fourth terminal, which we usually don't draw, which is between the device and the ground. It tells me some things about the nature of the gate here. The gate is actually connected to this terminal, which connects the ground in a form of a capacitance. So this is like having a capacitor here. That's why we also draw it like this. So in small frequencies, I expect no current to flow from the gate inside this device. Now if I am to draw the current and the VGS, which is the voltage and the drain minus the voltage at the source, I would notice this behavior. If I keep the gate constant and I don't really change it, from here to here, I have what I call the triode region, or which is also known as linear region. Linear because from here to here, this seems to be a constant, a linear relationship. In some books, you will see this operation, this area of operation here only as the linear region, and it will call this as the parabolic region or the triode region. In some other books, you will see that all of this is called as a linear region, or all of it is called as a triode region. These terms are interchangeable. Just don't be confused with your academic sources. All right, the relationship between the drain source voltage and the core and the current is going to look like this. We have a dependence on the VGS and the VDS that gives us the current at the drain of the device, and we have some constant values here. These are properties of the device, mu n Cox, right? Again, the capacitance between here and the ground, mu n the mobility of the electrons. We have W over L, which is the width over the length of the device, and we have VTH, which is the threshold voltage of the device. This threshold voltage gives us the VDS responsible for the operation going from the triode region to the this constant current region. This region is called the saturation region. The current is constant, and it's only related to VGS, not VDS. This is important. This tells to me that this region is much more useful than this region. And from now on, we will assume that for a healthy nMOS device, we are working in the saturation region. All right? Only because there is only a dependence with the VGS. Now, in order to be in the saturation region, two conditions must be satisfied. VGS must be higher than VTH, and VDS must be higher than VGS minus VTH. That means that if the drain voltage was higher than the gate voltage, we would be in saturation, no questions asked. If the drain voltage and the source voltage would be the same, again, we would still be in the saturation region. If the gate voltage was higher than the source voltage, but not as high as VTH, would still be saturation region. Again, this is a difference between the bipolar junction transistor. But if the voltage was higher than the drain voltage by more than VTH, well, this would mean that we would be in the linear or the triode region. The device would be going crazy, would be not very useful, the gain would be tiny, the device would be dead. Now, if I solve for VGS of this equation, I get this, all right? It didn't do anything special. And now I'm ready to introduce what's called the transconductance of the device. The transconductance is given as the derivative of the current in respect to VGS. And I get three expressions for my transconductance. Why three? Well, if I solve it from here, I get that GM is obviously, all right, 2 goes down here, it cancels out with 1 over 2, mu n Cox W over L times VGS minus VTH. And now I can go and play around with this and get a direct relationship with the current ID. And I can also get a relationship between IT and VGS with the transconductance. This is very important as I have three expressions for VGM, one connected to the current, one connected to the VGS. By the way, this current is called ID because it flows into the drain, but it also gets outside and flows into the source too. So if I wrote it IDS, it would be the same thing. No current actually flows into the gate of the device. All right. Now, I don't need to remember all of this. I just need to remember that there is a relationship, a direct relationship between the transconductance and the current, a direct relationship between the transconductance and the VGS, and a direct relationship between the current and VGS, this in spite of whatever the properties of the device are, with exception of the VTH of the device. So the only thing I really need to remember from all of this is this equation. Really, yeah. I only need to remember this, and if I intuitively remember how to get these other expressions, I can just do simple math operations to derive them. Now, in reality, there is another property of the device, which is not making our lives easier, to say the least. Sometimes we omit it, sometimes we have to include it. This is called the channel length modulation. I'm not going to go into the physics and the details of why it happens. I will cover this in the other video that goes into the physics of the device. But what I'm going to do is I'm going to show you what it actually does to my my current that I measure from here to here. The current follows the triode region operation here as it was before. This doesn't change, and the channel length modulation appears only in the saturation region. It changes the saturation region current, and the current, instead of being constant in respect to the change in VDS, now it has a slight slope here, and it has some kind of relationship of a linear relationship, a linear dependence on it. We show it as lambda being different from 0, right? when the channel length modulation in your exercise is going to be 0, it would mean that we omit it. We don't care about it. But when it is different from 0, it means that it is important. This would change my equation here of IT by adding it and n1 plus lambda VDS here. And that's it. That's how that's basically how the saturation current changes. Obviously, this is bad, right? Because again, now I have a relationship between the drain source and the gate source and the current to the device. But if it's small, like the effects are not very, very tragic. Now, if I do the same things that I did before, again, I will get this little term here. I would get it here, I would get it here, and I would also get it here. If this lambda is equal to 0, again, we return to the previous operations. If it's not, we have to adjust for it here. Now we are going to look at the small signal model of the device. And before we do it, I will connect a small signal source here. All right, a few millivolts, let's say. And I'm going to connect two batteries here. This is a battery in reality, or connected like a common rail here. It's a battery connected like this, all right, with a positive terminal to the drain and the negative connector to the ground. And I connect them just to ensure that my device is in saturation. If we're not in saturation, the small signal model is useless, and we cannot write it like this. Right, we have a current connected, and current flowing from the drain to the source, obviously. And before I draw it, I will be sure to set all my DC sources to 0. That means that my batteries are going to be short-circuited, and my current sources are going to be open circuits. I don't have any current source here, but in case I had, because there are cases that we actually have current sources. So if I don't have a channel length modulation effect in my device, I will draw this very strange looking circuit. The gate and the source will have no direct connection, all right? I remember there is a capacitance here and no direct connection. There is a voltage difference between the gate and the source, VGS or V1. I write it V1 just so I don't get confused. And there is a current source, a dependent current source between the drain and the source of V1 GM. In case of lambda is equal to 0, in case we don't have channel length modulation, the drain is going to be connected to the ground, all right? You see it, why? Because this battery is going to be short-circuited. The source is connected to the ground, and the gate is going to connect to the variable signal, and this short circuit would be grounded. This is called as the AC ground. It's not really the ground, but it is working similarly to it, and it's only valid for the small signal model. There is a current obviously flowing from this grounds all the way to here and all the way to here. This V1 is going to, it happens to be in this case the same as the V signal, and this is going to make and change the current here. Now, in case we had channel length modulation and the lambda was not 0, we draw the exact same small signal model, but we'd also draw a resistance, which is called RO, between the drain and the source. Here, the RO is not infinite, all right? And we'd also draw some of the a current of the drain here that would be lost inside here. Again, they will both connect at the source and be the same at the output. But it's important to note that V1GM here is not the same as this V1GM, just because some of the current was drawn here. So V1GM here was ID, but V1GM here is not ID. Alright, this would connect and become the same ID later down the line. And that's it. Those are the basics of the MOSFET device in the context of a circuit. To find out more about the basics of the physics of a device and the CMOS configurations and other electronics concepts, subscribe to the channel so you don't miss these videos too. Study well and take care.